Hello everyone. Today I'm going to tell you about a few science theories and laws that you should know. First, let's make a general definition. A scientific theory often seeks to synthesize a body of evidence or observations of particular phenomena. It's generally, though by no means always, a grander, testable statement about how nature operates. You can't necessarily reduce a scientific theory to a pithy statement or equation, but it does represent something fundamental about how nature works. Both laws and theories depend on basic elements of the scientific method, such as generating a hypothesis, testing that premise, finding and not finding empirical evidence, and coming up with conclusions. Eventually, other scientists must be able to replicate the results if the experiment is destined to become the basis for a widely accepted law or theory. In this video, we'll look at some scientific laws and theories that you might want to brush up on, even if you don't find yourself, say, operating a scanning electron microscope all that frequently. We'll start off with a bang and move on to the basic laws of the universe before hitting evolution. Finally, we'll tackle some headier material, delving into the realm of quantum physics. The first theory I'm going to talk about, the Big Bang. If you're going to know one scientific theory, make it the one that explains how the universe arrived at its present state. Based on research performed by Edwin Hubble, Georges Lemaitre, and Albert Einstein. Among others, the Big Bang theory postulates that the universe began almost 14 billion years ago with a massive expansion event. At the time, the universe was confined to a single point encompassing all of the universe's matter. That original movement continues today as the universe keeps expanding outward. The theory of the Big Bang gained widespread support in the scientific community after Arno Penzias and Robert Wilson discovered cosmic microwave background radiation in 1965. Using radio telescopes, the two astronomers detected cosmic noise or static that didn't dissipate over time. Collaborating with Princeton researcher Robert Dicke, the pair confirmed Dicke's hypothesis that the original Big Bang left behind low-level radiation detectable throughout the universe.
Do you think there are more people in the world who know about the Big Bang Theory than the TV series The Big Bang Theory?
As long as we're talking about one of the greatest scientists who ever lived, let's move on to Newton's other famous laws. His three laws of motion form an essential component of modern physics, and like many scientific laws, they're rather elegant in their simplicity. The first of the three laws states an object in motion stays in motion unless acted upon by an outside force. For a ball rolling across the floor, that outside force could be the friction between the ball and the floor, or it could be the toddler that kicks the ball in another direction. The second law establishes a connection between an object's mass and its acceleration in the form of the equation Fm multiply m multiply af represents force measured in newtons. It's also a vector, meaning it has a directional component. Owing to its acceleration, that ball rolling across the floor has a particular vector, a direction in which it's traveling, and it's accounted for in calculating its force. The third law is rather pithy and should be familiar to you. For every action, there is an equal and opposite reaction. That is, for every force applied to an object or surface, that object pushes back with equal force.
Who feels sorry for Wile E. Coyote, who spent years trying to catch the Roadrunner? Don't we all spend our lives chasing impossibilities?
Our next theory is the special relativity by Albert Einstein, the most popular scientist in the world. In physics, the special theory of relativity, or special relativity for short, is a scientific theory of the relationship between space and time. Revolutionary insights about the nature of light, time, and energy as Einstein became better known in the scientific community. He began receiving requests to write about his new theory for journals and books. In 1912, he was asked to contribute several chapters on relativity to a book. The result is this 72-page manuscript, because he did not save drafts of his 1905 papers. This manuscript is the earliest known description of relativity in Einstein's hand. Pages from the 1912 manuscript on the special theory of relativity. Einstein first published his special theory of relativity, which describes his revolutionary ideas about light, time, and energy in 1905. He revisited the theory in this 1912 manuscript when he was asked to write several book chapters. The outbreak of World War in 1914 delayed publication, and when the project resumed, Einstein considered this manuscript outdated and it was never published. Nevertheless, the manuscript represents an important stage in Einstein's work. The draft focuses on the special theory of relativity, which applies to the special circumstance in which observers making measurements do not change speed or accelerate, but this draft also hints at how Einstein developed his more comprehensive general theory of relativity. That theory, finalized in 1916, applies to all observers, even those undergoing acceleration, and is actually a theory of gravity. Each page of the 1912 manuscript on the special theory of relativity reveals an exacting mind at work. Mathematical equations have been altered, words have been crossed out, and entire paragraphs have been rewritten. When Einstein was asked to write these chapters, he decided to do more than simply summarize relativity. Instead, he derived from first principles the basic tenets of his influential theory about light, time, and energy. In the process, he refined his ideas even further. For example, he adopted a novel four-dimensional mathematical system in this manuscript to explain portions of special relativity. Physicists refer to this four-dimensional system as space-time, the union of three-dimensional space with a fourth dimension of time. Observation of MIC2 in the 1912 manuscript on the special theory of relativity. The 1912 manuscript on the special theory of relativity includes Einstein's most famous equation, EmC². In this draft, however, the equation, which demonstrates that mass is a form of energy, appears in a somewhat different form. Originally, Einstein used the variable L for energy, while L stood for Lagrangian, a general form of energy. Later, he crossed out the La and changed it to E. The equation shown here also includes several extra terms. Technically, the short version of the equation, EmC2, applies only when an object is at rest. The longer, more complete form of the equation included in this manuscript applies to moving masses as well. Thank you for watching. See you in the next video.
I'm taking shots at the enemy. I'm gonna make it to the top, leave a legacy.